Okay, so we're now going to get into talking about some properties of triangles, and more importantly, the ideas of similar triangles, which you're going to notice one of the nice concepts that we'll see trigonometry depends on has a lot to do with similar triangles. So before we do that, let's kind of just quickly identify the types of triangles that we may encounter. So if we're talking about the different types of triangles, and usually these triangles are defined either by their sides or by their angles. So these that I mentioned here are going to be defined by their angles. So when we say obtuse, if we talk about an obtuse triangle, this is a triangle that has one obtuse angle. And we'll see that shortly in a few minutes. We'll see why it's impossible for a triangle to have more than one obtuse angle anyway. So this is what an obtuse triangle looks like. And then we have acute triangles. And acute triangles are, you'd see that all angles are acute. So it's kind of something like this, where all of the angles are acute. Okay, and then lastly we have a right triangle, which we know that this will have a one right angle, and it'll look something along the lines of that, right? So kind of it'll be a right triangle here. So obtuse, acute, and right triangles. Okay, now we also have triangles that we could define or identify through their sides. So for example, if we have an equilateral triangle, this is basically a triangle where all sides are equal. So in other words, we'll get something that looks like this, and we usually use this notation to say, look, all three sides are the same length. And then we also have isosceles. And isosceles would mean basically only two sides are equal. And that would look something along the lines of this, where you have these two sides are equal, and this third side doesn't necessarily have to be the same, right? So that's why I'm putting two lines here. I'm saying, look, these two are the same, that one's not necessarily the same. And then the last type of triangle we have is a scalene, which a scalene, none of the sides are equal, so no equal sides. So maybe something like this. Something like that, where none of the sides are the same length. Okay, so that's what a scalene triangle is. So these are the classifications of the triangles. We have obtuse, acute, right, and then in terms of the sides are concerned, we could say equilateral, where all the sides are the same, isosceles, only two of the sides are equal, and scalene, which none of the sides are equal. Okay, so with that said, now let's get into our properties of triangles. And let's kind of start off with a picture. So I could say, look, given a triangle ABC, so let's kind of draw it off on the side. I'm just going to draw just some generic triangle. So let's call this triangle A, B, and C. And usually the way we label the sides, if this is angle C, the side opposite angle C, which is here, that'll be side C. And angles are usually with capital letters, sides are with lowercase letters. So if this is angle A, side A is always identified opposite of angle A. So if this is angle A, if I move to the opposite, that's side A. If that's angle B, this is side B, right? So that's usually how we label our triangles. So here are some properties about these triangles. We can say that the sum of the angles, of any triangle is 180 degrees. So in other words, I could care less which triangle we're looking at. So even if this triangle we have on the right side, we know that if I take angle A plus angle B plus angle C, those measures are always going to add up to 180 degrees. So that's a fact. Anytime we have a triangle, the sum of its angles are going to be 180 degrees. And then we have the next property, which says the sum of any two sides of a triangle is greater than the third. So in other words, and this, if you ever find a triangle where if you take any two sides, you add them together and it's not greater than the third side, then that's not a triangle, right? So that cannot work. So this is kind of this is something known as like the triangle inequality, that is a very important concept in mathematics that's used quite a bit in a lot of theory and proofs. So here's what I know. If I take any of the two sides, it doesn't matter. So here's what I know. If I take side A plus side B, that's going to be greater than side C. And it doesn't matter which two sides you pick. So for example, I could say side A plus side C, that's going to be greater than side B. And then lastly, what's the other combination? We could say side B plus side C, that's going to be greater than side A. So these are all facts. These are all true. So if I really have a triangle, if I take any two sides and I add them together, that will be greater than the third side. Okay? So the third property is the following. Larger angles are opposite larger sides. So what does that mean? Remember how we said this angle C, the way I identify side C is opposite angle C. So here's what we can say, for example. If angle C is greater than angle A, so if angle C is greater than angle A, then obviously the side opposite angle C, which is side C, must be greater than the side opposite angle A, which is side A. So what we're saying is if angle C is greater than angle A, then side C must also be greater than side A. Okay, so that's kind of what we're basically stating here. If you have two angles and one angle is greater than the other angle, then the side opposite the greater angle is greater than the side opposite the smaller angle, right? So that's kind of what we're saying here. Okay, so with that said, let's look at our first example with where we'll put into these properties into use. So for example 1, we're going to say find the unknown angle measure of the triangle. Okay, and this triangle is, this is 3 alpha, 2 alpha, 5 alpha. Okay, so notice how I have an unknown, right? And this unknown is the Greek letter alpha. So what we're trying to do, we're trying to figure out what the measure of all of these angles are. Well, if I could figure out what alpha is, then I could figure out the measure of each angle. So for example, if alpha is 10, then this would be what? 2 times 10, which would be 20. Then this would be 3 times 10, which would be 30. This would be 5 times 10, which would be 50. So think about it. Which property would we use to be able to solve for alpha? Well, if you look at the properties that we talked about, I believe it was the first property which said no matter what it is, what kind of a triangle it is, if we add up all the angles, that should always add up to 180 degrees. So notice how that's a nice equation to use because it allows me to kind of come up with a formula. So I know that if I take 5 alpha plus 3 alpha plus 2 alpha, which these are the three angles of this triangle, and I add them up, I should get 180 degrees, obviously, which notice how now I'm able to solve for my unknown, alpha. And once I know what alpha is, then I could solve for this triangle, basically, or the angles. So what do I get? 5 alpha plus 3 alpha is 8 alpha plus 2 alpha is 10 alpha equals to 180. Divide by 10, which implies alpha equals to 18. If alpha equals to 18, then what are the angles? Then 2 alpha, which is 2 times 18, which will be 36 degrees. What else? 3 times alpha, which would be what? 3 times 18, which would be 54 degrees. And lastly, 5 times alpha. So 5 times 18 would be what? That would be 90 degrees. And there you have it. Okay, so these are my three angles as we were asked to find. Except we went after the unknown first. Okay, so let's look at our second example. So for example 2, the three sides of a triangle are A equals to 27, B equals to 15, and C equals to 22. And 2 of the angles measure 71 degrees and 42 degrees. Okay, so for part A, find the measure of the third angle. Okay, which this shouldn't be bad, because what is it that we know? If I have 2 of them, so let's call the third angle, let's call it x for now. But what do I know? If I take x and I add 71 and 42, and since these are all the angles of a triangle, we know that they should add up to 180. So let's say let x equal to the third angle. So then we know what? X plus 71, so let's say x plus 71 plus 42 has to equal to 180, which gives us a nice clean way of solving for x, which then that means x plus 71 plus 42 is what? That's 113 equals to 180. Subtract 113 from both sides, and you get x equals to 67 degrees. So we found the third angle to be 67 degrees. So what's part B saying? Name each angle using the correct, so we're going to say name each angle using the correct capital letters. Okay, so this is important, right? Because here's what we know. Remember what we just talked about. The largest angle should have the largest side opposite to it. So here's what we know. If side A is 27, side B is 15, side C is 22, see, the sides have been labeled. Now we need to figure out which angle is which. So from these sides, what's the largest one? The largest one is 27. So what does that mean? Angle A should be my biggest angle. Remember one of the properties we talked about? The largest angles have the largest sides. So since this is the largest side, this will be the largest angle. So from my angles, which one is the largest? 71 degrees, right? So A will be 71 degrees. What's my second largest side, which would be 22, which means angle C should be my second largest angle, which is what we found to be 67, right? Because the three angles are what? 71, 42, and 67. Okay, and so since B is the shortest side, the angle opposite the shortest side will be the smallest angle, which is 42 degrees. And there you have it. We're able to identify the missing or the angles appropriately. Okay, so let's get on to the last concept of this section, which has to do with similar triangles. Okay, so we can say, so how do we know triangles are similar? Two triangles are said to be similar if their corresponding angles are equal. Okay, so what does that mean? In other words, we could say, look, that is, if triangle ABC and triangle DEF are similar, and notice how we've written them, A, B, C, D, E, F. If these two are similar, then the order matters. Then what does that mean? Look, what letter comes here first? A. What letter comes here first? D. So A and D must be equal. Because if they're similar, then the order matters, because corresponding means they have to be in the same order, or the order is what I'm following. So we would say that then angle A has to be equal to angle D. Then what angle comes next? Angle B and angle E. Angle B has to be equal to angle E. And what else? And angle C has to equal to angle F. So the order is what matters. So visually speaking, if you think about it, if I do something like this, let's say A, B, C, and let's do something like this, D, E, F, and you see that this is, I don't know, I'm going to make some numbers up. This is 100 degrees, that's 100 degrees. This is 30 degrees, and this is 30 degrees, and this is 50 degrees, this is 50 degrees. Now, how come we know that these triangles are similar? Because look, the angles are all the same, except what are my corresponding angles? See, the A and D are corresponding because they're both the 30s. B and C are corresponding because they have the 50s, or B and E, sorry, this is an E. And then C and F are corresponding because they have the same angle. So how they're drawn, we don't care. It's more about, we care more about the angles that are matching up. Okay, so just keep that in mind. So what happens if triangles are similar? Here's the important part. Also, if two triangles are similar, then their corresponding sides are proportional. So what is it that I'm saying here? If I have similar triangles and I take their corresponding sides, so for example, since these two angles and these two angles are equal, this side and this side is in their corresponding sides. If I write a ratio where I take one side divided by the other, and then I take the next two corresponding sides and I find the ratio where I take one divided by the other, the ratio will stay the same. That's what we mean by they're proportional. So here's what I mean. For example, if I have a triangle that looks like this, A, B, and C, and I have another triangle that looks like this, which this is bigger, which it doesn't matter, right? This is D, E, and F. Let's pretend that they're similar. So, and let's assume that A and E are the same, C and D are the same, and B and F are the same. So those angles they're all corresponding to one another. So in other words, here's what I'm saying. This is 1, this is 2. Now look at what the proportion is. Now it doesn't matter what order we divide them in. You could say 1 divided by 2 or 2 divided by 1. But let's go this way. 1 divided by 2, that's 1/2. And then if they're in proportion, or if they're similar, which they clearly are because the angles are congruent, if this is 3, this side, which this is the corresponding side, that has to be a 6. How come? Because the ratios always have to be in proportion. Because what's 3 divided by 6? That's the same thing as 1/2. 1 divided by 2, which is 1/2. So my ratio, or what I'm saying is, whatever these sides are, their ratio should always be 1/2. If that's not the case, or the ratio is not always the same, then the triangles are clearly not similar. So for this case, if this is 5, this has to be a 10. So in this case, notice how 1 divided by 2 is 1/2, 3 divided by 6 is 1/2, 5 divided by 10 is 1/2. So notice how the ratio doesn't change. They're proportional, right? They end up being the same. So with that said, which that's a nice fact that we know, because we could always use this to help us solve certain problems. We know that they must be true. So let's move on to our last example where we'll see how this works. So we could say use properties of similar triangles to find the lengths of all 3 sides of the smaller triangle. Okay, so let's look at this picture here. So what is it that we have? We have x plus 1 is that side. This will be 6. That's a right angle. That's theta. And then we have another triangle that looks like this. That's theta. That's a right triangle. This is 6. This is 3x. Okay, so one comment I want to make. See, right away, just by looking at this, how do we know that these two triangles are similar? Well, look, that's a 90-degree angle, that's a 90-degree angle. So these two are corresponding. This is theta, this is theta. And since we're using the same variable for both of these, then we're assuming that they're the same. So these two are the same. So guess what? If two of the angles, or two corresponding angles of a triangle are congruent, or they're equal, then the third one is guaranteed to be equal also. How come? Because these angles add up to 180, right? This plus this adds up to 180. This plus this adds up to 180. So if these two are the same, then these two also must be the same. So look, if these two are the same, and these two are the same, then these two must be the same, right? So to show two triangles are similar, in all honesty, all you really have to do is show that two of the corresponding angles are equal. Then that's good enough as showing that then the third ones are automatically equal also. So these two triangles are definitely similar. How come? Because the corresponding angles are congruent, or they're equal. So now we need to kind of figure out what the corresponding sides are, because then we can figure out what the measure of each side is, or what the ratio is. So what I tend to do is, see the way these are drawn, which there's nothing wrong with these, but anytime I see two triangles are similar, I redraw them. I redraw them in a way where it's very easily can be seen where the corresponding sides and angles are. So I'm just going to redraw this just so the angles of this match up with the angles of that. So they're basically all oriented the same way. So this guy I'm going to keep the same way. I'm going to say this is 90 degrees theta. This is x plus 1, 6. And I'm going to grab this triangle and I'm kind of going to rotate it. So if I rotate it and I get it to stand upright, kind of like this guy, where the angles are matching up. So this guy is now here. This angle is now there. This is now here. This is now there. But the reason why I redrew this, because now I could easily see what the corresponding sides are. Here's what I know. This divided by that ratio should be what? The same as this divided by that. Hopefully you guys know why, or you understand why, because if you look earlier, what did I say? This divided by that should be the same as this divided by that. Look, 5 divided by 10 is a half. 1 divided by 2 is a half. Now, why is that important? Since these triangles are similar, that's going to help me find x. And once I find x, then I'll be able to figure out exactly what the length of this missing side is. So here's what I do know. We know, since these two triangles are similar, so since the triangles are similar, this implies, what do I know? X plus 1 divided by 6, x plus 1 divided by 6 should be the same thing as what? This divided by that should be the same as 6 divided by 3x. 6 over 3x. Okay? So now I could solve for this by using, cross multiplication. So if I cross multiply, what do I get? Let me turn this to the other page. So what would that be? It'll be 3x times, I believe it was x plus 1 equals to 6 times 6, which is 36. So all I really did was, since we had a fraction, I just used cross multiplication to solve for this, right? I mean, there's different ways you could solve for it, but that's what I did. So now what do I notice? I'm going to try to solve for x here, and I'm going to distribute the 3x, which what does that give me? 3x squared plus 3x equals to 36. And it looks like I'm going to try to solve this by factoring, because notice how I have x squared and an x. So the first thing I see that I want to do is I want to bring the 36 over if I want to solve by factoring. So subtract 36 from both sides. So I get 3x squared plus 3x minus 36 equals to 0. And another thing that I see that's nice here is I could divide everything by 3 because they all have a factor of 3. So if I divide, which remember this is an equation, as long as I consistently divide everything, that I could do. So then what does this become? X squared plus x minus 12 equals to 0. And sure enough, I could try to solve this by factoring, right? Which that factors, doesn't it? It factors to what? X plus 4 times x minus 3 equals to 0. And then when I solve for x, what do I get? X plus 4 equals to 0, or x minus 3 equals to 0. But if I subtract 4 from both sides, I get x equals to negative 4, or x equals to 3. Okay, now let's be careful. What would be the problem? See, I can't accept x equals negative 4 as an answer. Okay, I'm going to reject this. How come? Because look, if I let x equal to negative 4, and now let's go back to our original picture. If I plug in negative 4 for x here, what do I get? Negative 4 plus 1, which gives me negative 3. Notice how this is describing the length of a side of a triangle. The length of a side of a triangle could never be negative, right? So we could see that I can't have a side of a triangle that measures a negative length. That's why we have to reject the negative 4, which that one doesn't work, but x equals 3 does work. So if x equals 3 works, and if I come back to this original picture here, what is it that we're saying? We want to find the lengths of all three sides of the triangle. So let me grab the smaller triangle and translate it back over here, because we only care about the smaller triangle. If you remember, it was what? Theta. This is x plus 1. And then what else did we have? This was 6. Okay, so now I know what x is, so I have this side, which if x is 3, so this now, let me redraw this. It becomes what? If this is 3, this becomes 4, 6, and then we just need to find this side, which let's call this A for now, which we could find that side, can't we? because we have this is a right triangle, and if you remember in the last lesson, what did I say? If we have a right triangle and two of the sides are missing, unfortunately this is not a 30, 60, 90 or a 45, 45, 90, or at least I don't know at this point, but I could still use the Pythagorean theorem. So what does the Pythagorean theorem say? The sum of the two sides, two legs of a right triangle, squared and added, or the sum of the squares of the two legs of a right triangle equals to the square of the hypotenuse. So a squared plus 4 squared equals to 6 squared. Now I could solve for this, which is what? A squared plus 16 equals to 36. Subtract the 16, I get a squared equals to 20. Square root it. And since the a is the length of a side, I'm not going to put plus or minus because I only want the plus. Because if you remember, anytime you take a square root, you put plus minus. In this case, we don't need to because the minus would mean it's a negative length, but that makes no sense as far as the length of a side goes. So this is a is rad 20. And if we simplify the square root, what is that? 20 becomes 4 and 5, but I know rad 4 is 2, so I could pull out a 2. So this would be 2 rad 5. So this side is 2 rad 5. And there you have it. We found all the missing sides of the smaller triangle. Okay, so this takes care of this section. Similar triangles are going to be very, very important, especially because their ratios always stay the same, and that's going to play an important role in this class. And you'll see as we get into our trig functions, as we will in the next lesson. But this takes care of this lesson. So once again, please don't hesitate to reach out to me if you have any questions relating to the notes.